This is Physics 2212 Lab 4 bar magnets. The purpose of this lab was to investigate how distance affects magnetic field of a small magnet, measure the magnetic field on axis and off axis, and then model the magnetic field of a bar magnet and compare the measured fields and the computed fields. The magnitude of the magnetic field increases as distance decreases, and the magnetic dipole moment was calculated to be 3.4. The measured off-axis magnetic field is 1.757 e to the negative 4, and the simulated off-axis magnetic field is 1.00741 e to the negative 4. The key concepts were the Biot-Savart law, which equation is in the second bullet point. And then we can calculate the magnetic field of the dipole from this with that equation in the fourth bullet point, where mu is I times the loop area, which is I pi r squared. And then B bar is K r to the n, where K is a combination of the magnetic constant. So that was all the equations that we used in this lab. The experiment, so the system was the magnetometer, the surroundings were the bar magnet and Earth because they exert a magnetic force on the magnetometer. We oriented so that the magnetometer app had an x component of 0 and then found the app magnetometer chip, as you can see with that tape on the phone. For the on-axis field, we recorded the distance where the magnetometer x component reads 20, 40, 70, 120, 170, and 220, and we repeated the experiment for each value 3 times and took the average of those. So we just moved the magnet until the magnetometer read one of those values, whichever one we were testing at the time. Part 2 of the experiment, we measured the off-axis field. So we measured the on-axis distance when the net magnetic field read 100, and then we recorded the y component of the Earth's magnetic field and moved the magnetometer the recorded distance in the y direction. We recorded the components of the magnetic field there and then adjusted the y component for Earth's magnetic field using that magnetic field that we observed on the on-axis field. And then we repeated that a total of 3 times and took an average again. So here are the experimental results. As you can see, I plotted a regression graph in our Excel spreadsheet, and all the values are calculated there. The regression line for the data is the natural log of the magnetic field equals the natural log of k plus n ln r. The slope would be n and the y-intercept is ln k. So we can solve for k using E as shown in the picture. And then using k, we can solve for the magnetic dipole moment using that equation listed in the bullet point, which is all shown in this picture of my handwritten calculations. And then the corrected magnetic field for the y direction was calculated by subtracting the value we measured for Earth's magnetic field from the measured y component at the off-axis point. The observation, so as the magnet moves closer to the magnetometer, the observed magnetic field increases in the x direction, and then when the magnet is far from the magnetometer, the x component is 0. Here is some screenshots of my code. So this first image right next to the title is calculating the magnetic field function, and then the big picture is the creation of arrows for our model. And then the picture at the bottom is creating the 45-degree observation location. Here is the output of our code. As you can see, it looks very similar to the dipole field that I pictured on the physics principles slide. So as the distance between the magnet and the magnetometer increases, the magnetic field decreases, as we observed. The magnetic dipole moment is 3.4. And then the experimental and simulated off-axis fields are just slightly different. The measured off-axis magnetic field is 1.757 e to the negative 4, and the simulated off-axis magnetic field is 1.00741 e to the negative 4. So possible error that could account for this slight difference is that other magnetic fields were interfering with the results, like laptops, devices, or wires. There's inconsistent placement of the magnetometer, so Earth's magnetic field didn't cancel out like all the way. The surface could have like not been completely flat, so then there's like a z component contributing to the net magnetic field. And then there could be inconsistencies with the magnetometer, like calibration issues, or there was measurement error when finding distance, so that would account for like human error. What if you hadn't oriented your experiment to compensate for magnetic north? So the observed field would have been different, not accounting for Earth. The x and y components would have been different, but since the phone is on a flat surface, the z component would have little change. And then what if you were to stick two identical magnets together end to end and run the experiment again? The net magnetic field would increase since there's now a combined field from the two magnets, and then it would probably around double since it's the same magnet, they're identical. And then the distances would increase due to the stronger magnetic field. Okay, thank you so much.